In this video, I'm going to show you guys a few basic unimultipliers and a more complicated unimultiplier. I cannot show you every single instance of every single unimultiplier situation, but the practices and strategies are still the same. In this basic situation, we are going to predict the mass for a given volume of 400 cubic centimeters of steel. But before we do this, I want to remind you guys of the basic setup of a unimultiplier. Typically, a unimultiplier works left to right, and you always typically start off with some measurement that you have in your possession, and you take it times some known ratio. These known ratios could be common knowledge things like for every 1 meter there's 100 centimeters, or in the case of this situation, we know that for steel there's 7.85 grams for every 1 cubic centimeter. So that's a mass to volume ratio. So anytime you're doing a problem that requires mass and volume, you're going to need a density for that substance. But after you take what you have times some known ratio, you may need to do more than one known ratio tagged in there to cancel all the units you no longer want. And then eventually your goal is to get to some unit quantity that you want. So let's go back to the problem. I have 400 centimeters cubed, and I need to start canceling out the centimeters cubed because I no longer want a volume measurement. I want to get the mass measurement that goes along with 400 centimeters cubed. So a common knowledge ratio I have from class is the density of steel. I'm going to use the density of steel, and I'm going to place the 1 centimeter cubed in the denominator so that the centimeters will cancel back through the act of division. I'm going to put the 7.85 grams in the numerator, and those are the units that will stay now that I'm trying to get the mass as a prediction. Make sure you cancel out your units that cancel out through division, and then multiply across for the 400 times 7.85, and you should get approximately 3,140 grams of mass. Now you can do the same thing if you have a mass and you want to predict the volume. It's just the opposite, but you use the same ratio. So for instance, if I had 15 grams of mass of steel, how much volume would that be? I can still use the same ratio of 7.85 grams for every 1 cubic centimeter, but you guys got to make sure you flip that and the units you no longer want are placed on the denominator so that they cancel back to the numerator on the beginning quantity. Put the other part of the ratio in the numerator and simplify. Swipe the grams and take 15 across the top times 1, so that's 15 cubic centimeters. But you know you still got this 7.85 laying around, so you have to drag it over with no units. And a side note, make sure you do not take the 15 or any other number that you start with and drag it down and multiply across the bottom. There's technically a little ghost 1 hanging out under here, and with these ratios you multiply across the top and you only multiply across the bottom. Do not try to do any kind of shortcuts like cross multiply and divide. That's inappropriate to do at this point. So the ghost 1 times that 7.85 just brings the 7.85 over to the denominator. Now if you finish this out and do 15 divided by the 7.85, you should get approximately 1.9 centimeters cubed. So 2 examples of a single step unit multiplier, about as simple as they get. Now I'm going to get you guys to do a more complicated multi-step unit multiplier. In this example, we're still going to do something related to density where we're predicting the volume. In this prompt it says predict the volume of meters cubed for 15 kilograms of mass for aluminum. So this one's going to be multi-step. The first thing you guys have to realize is that you're dealing with a situation where you've got volume and mass again, and so somewhere you have to have a density. So I've got a density for aluminum from class that we use that we said was approximately 2.7 grams for every 1 centimeter cubed. But you also have to realize not only is this a density themed problem with mass and volume, you have to realize that the units that we want to end up with is meters cubed, and we're starting with kilograms. So I already know that the units that we want to get from and get to do not play nice with the grams and the centimeters cubed family units. So we're going to have to change those throughout this process. But again, we're still going to start off with some quantity that we have times some known ratio. And we're going to do it several times in order to get what we want. So if we follow this little practice mantra of have times known ratio to get what we want, we just plug in the 15 kilograms because that's the mass we have. But you must realize that we cannot directly use the density because the density is in grams. So we have to do a unimultiplier where we get out of kilograms into grams. And in order to do that, you need to know some common knowledge things. And that for every 1 kilogram, there's 1,000 grams. I expect that to be common knowledge and students to know that. So I'm going to use that ratio and flip it so that kilograms is in the denominator and grams is in the numerator. Therefore, the kilograms cancel out. And I am not going to stop and do the math calculations. I'm going to continue on the storyline and add another known ratio. Because now that I'm in grams, I can get closer to the volume that I want to predict by using the density now. Now the grams units play nice. But I need to put the 2.70 grams in the denominator and the 1 centimeter cubed in the numerator. Now the regular grams cancel. And now I'm in a volume. Centimeters cubed is a volume. So we're close to predicting the volume, but we need to make sure we continue to get it into meters cubed. Right now we're only in centimeters cubed. So in order to do that, we have to cancel the centimeters cubed. And a side note, you need to remember that centimeters cubed is built from centimeters times centimeters times centimeters. So we have to cancel out a centimeter unit 3 times by using a common knowledge ratio that everyone should know how to use. And that's for every 1 meter, there's 100 centimeters. Since centimeters family is in the numerator, I need to put my ratio flipped so that centimeters are in the denominator so that they backwards cancel back to this numerator. So this 1 centimeter unit cancels only one of these centimeters cubed units. So that's one of them gone. So I need to do it again and repeat. And the work I'm doing on the right with the centimeters times centimeters times centimeters, that's just for teaching purposes. You do not have to do this on your work. So now if I complete one more ratio, I will have finally canceled out the very last centimeter. And now if you do the math, the units would be meters times meters times meters, which is meters cubed. So that's our Q. That's the units we want. Now we need to execute the math. And remember, when you do the math on this in the multiplication, you're multiplying across the top. You are not multiplying the 15 times the denominator, but you are going across the denominator all the way. And if you multiply across the top and you multiply across the bottom, you end up with 15,000 meters cubed divided by 2,700,000, and simplify that one more step. You should get 0.0056 meters cubed. Your success on these multi-step problems is going to be up to how well you identify what quantities you're starting with and you have, where you want to end up with the want, and then what ratios do you have, whether it's a density or some common knowledge ratios over here on the left, or on the right, excuse me. I'm going to move on to a more complicated problem that has several steps involved, including basic algebra. This final example is going to include using the unimultiplier strategy to change units into family units that can work together well. But it's also going to use basic algebra with rearranging and solving for variables that are missing from simple equation, like volume equals length times width times height for simple objects like a block. Again, some of the work we've done in class requires you to do different volume equations for objects like cylinders. But in this case, we're going to keep it simple with the multi-step problem and use a rectangular shaped prism. The directions say they want you to predict the height of a block of aluminum if it has the following dimensions. So we've got the length of 11.7 inches, and we've got a width of 4.2 centimeters. So right off the bat, I already see that my units for the length and width do not play nice. One is in the units of inches and one's in the unit of centimeters. And then the volume's given to you at 250 inches cubed. So the problem wants you guys to predict the actual height of this plate. In order to do that, we simply need to use this volume equation, because we know the volume, we know the length, we know the width, we just don't know the height. So all we got to do is plug in the quantities we know and solve for the height. But you can't touch this equation until all the units are in a similar family. So you have some choices. You could either change the inches and inches cubed to centimeters and centimeters cubed, but that would be 2 unit multipliers. You could also just simply change the centimeter for the width to the inches, so they're all in the inches family. But in order to make this a little bit more challenging, let's take and turn this into the height in feet. So I'm going to go ahead and just do a one-step unimultiplier that gets the width into inches, so it matches the family of the length and the volume. So I'm going to do a small, simple one-step unimultiplier. I'm going to use the whole take what you have times your known ratio to get what you want. So I'm making a problem-solving decision to convert these units to friendly units for inch family. I know there's a common knowledge ratio that for every 1 inch, there's approximately 2.5 centimeters. That's not necessarily common knowledge, so that may have to be given to you, or you might have to look it up. I put the centimeters in the denominator so that the centimeters cancel. And now I'm no longer in the centimeter family, but now I'm in the inch family once I do the math. So 4.2 inches, bring over the 2.5. 4.2 divided by the 2.5 gets you 1.68 inches. So now that I'm in all the inch family, I can now go back and use my volume equation. And if you remember from the prompt, the volume was 250 inches cubed. The length was 11.7 inches. The width I just converted to 1.68 inches. And the height, we don't know. We're trying to estimate the height. So the best way to do this is to start simplifying and isolating the variable for height. In order to do that, we need to multiply the 11.7 inches times the 1.68 inches. And I'm going to rewrite this and track all my work, and I want you guys to do the same thing so that if you make an error, we can trace back to where your error might have occurred. So I have approximately 19.66 inches squared, because inch times an inch is inches squared. Bring down the variable for height. Now we're a step closer to isolating the h. The 19.66 inches squared is connected to the height through multiplication. Most students would say to divide that to free up the height. So 19.66 inches squared cancels those out. But since we just manipulated the equation on the right hand side, it's no longer a true statement, so we must manipulate the left side as well to keep it the same. Now it's interesting here, if you got inches cubed in the numerator and inches squared in the denominator, which units cancel? Two of the three cancel. So inches squared down here, but only two of these up here cancel. So we're left with the inches, which is a fine unit for the height. So if you take 250 cubic inches and you divide it by the 19.66 square inches, you should get something close to 12.72 inches of height. So be aware that some problems you're going to do in class are going to require you to convert units in order to use another equation or another relationship like a volume equation.